What if I told you that, right now, at this very instant, you're living in the past, not metaphorically, not philosophically, literally, physically, scientifically in the past. The present moment you think you're experiencing doesn't actually exist the way you think it does. And the reason why will fundamentally change how you understand reality itself. Look at your hand right now. Go ahead, look at it. That hand you're seeing? You're not seeing it now. You're seeing where it was a few nanoseconds ago. The light bouncing off your skin had to travel to your eyes. And light, despite being the fastest thing in the universe, still takes time to travel. You've never actually seen your hand in the present moment. You've never seen anything in the present moment. In fact, there might not even be a universal present moment at all. Here's where it gets absolutely insane. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes ago. The nearest star system, Proxima Centauri, 4 years ago. But here's the mind-breaking part that most people never consider. This isn't just about looking at distant objects. This limitation applies to everything. Your friend sitting across from you at dinner, you're seeing them nanoseconds in the past, the words coming out of their mouth, you're hearing them milliseconds after they spoke them. Every single interaction you've ever had with another human being has been with a version of them that no longer exists by the time you perceive them. The speed of light doesn't just affect what we see in space. It defines the very structure of what we call now. And once you understand this, you'll never think about time, consciousness, or reality the same way again. Over the next 3.5 hours, we're going to journey deep into one of the most profound questions in all physics and philosophy. We're going to explore how Einstein proved that your now is different from everyone else's now, how this reshapes everything from free will to the nature of existence itself, and why some of the smartest physicists alive today think that the past, present, and future might all exist simultaneously in what they call the block universe. Before we dive into this reality-shattering journey, smash that like button and subscribe, because you're about to have your mind completely reconstructed. And I'm genuinely curious. Drop a comment telling me what country you're watching from and what time it is for you right now. Because as you'll soon discover, your now might be fundamentally different from mine in ways that go beyond just time zones. Let's begin by building our foundation, because you need to understand what light actually is before we can understand why it breaks the concept of now. To understand why the speed of light defines the present moment, we first need to grasp what light actually is and why it behaves so strangely. Most people think of light as just the stuff that lets us see, but light is something far more fundamental to the universe itself. Light is an electromagnetic wave, a ripple in the electromagnetic field that permeates all of space. When you flip a light switch, you're creating oscillating electric and magnetic fields that propagate through space at an exact speed, 299,792,458 meters per second in a vacuum. We usually round this to 300,000 kilometers per second, or about 186,000 miles per second. But here's the first twist that most people don't realize. Light doesn't actually travel at the speed of light most of the time. When light moves through any material, water, glass, air, even the vitreous humor in your eyeball, it slows down. The light bouncing off the screen and entering your eye right now is traveling slower than the cosmic speed limit. Only in the perfect vacuum of empty space does light reach its maximum speed. This maximum speed isn't just a property of light, though. It's a property of the universe itself, a cosmic speed limit that nothing with mass can ever reach, and that information itself cannot exceed. Think of it like this. Imagine the universe is like an enormous ocean, and the speed of light is like the maximum speed that waves can travel across that ocean. Just as waves in water have a maximum speed determined by the properties of water itself, light waves have a maximum speed determined by the properties of spacetime itself. The speed of light is literally woven into the fabric of reality. It appears in fundamental equations throughout physics, in Einstein's famous E equals mc, in Maxwell's equations describing electromagnetism, in the mathematics of quantum field theory. This speed, designated by the letter c in equations, is a constant that describes how space and time relate to each other. Now here's where things get interesting. For most of human history, people assumed light traveled infinitely fast. Aristotle believed light was instantaneous. When you opened your eyes, you simply saw there was no journey, no travel time. This made intuitive sense because light is so fast that over human-scale distances, it might as well be instantaneous. The light from a lamp across the room reaches your eyes in about 10 nanoseconds, 10 billionths of a second. Your brain can't detect that delay, so it feels instant. The first person to seriously question whether light had a finite speed was Galileo Galilei in the early 1600s. He designed an experiment where he and an assistant would stand on distant hilltops with lanterns. Galileo would uncover his lantern, and as soon as his assistant saw the light, the assistant would uncover his lantern. By measuring the time delay, Galileo hoped to calculate the speed of light. The experiment failed because light is simply too fast to measure this way over such short distances. The delay Galileo was trying to measure was a tiny fraction of a second, far too quick for human reaction times to detect. But Galileo's failure was important. It proved that if light did have a speed, it was enormously fast. The breakthrough came in 1676 from an unexpected source, the moons of Jupiter. Danish astronomer Ole Rachmer was studying Io, one of Jupiter's largest moons, which orbits Jupiter every 42.5 hours like clockwork. Rachmer noticed something strange. The timing of Io's eclipses behind Jupiter would drift depending on where Earth was in its orbit. When Earth was moving toward Jupiter, the eclipses appeared to happen slightly earlier than predicted. When Earth was moving away from Jupiter, they appeared to happen slightly later. Rachmer realized this wasn't because Io's orbit was changing. It was because light from Jupiter had to travel different distances to reach Earth, depending on where Earth was in its orbit around the Sun. When Earth was closer to Jupiter, light had less distance to travel, so we saw events sooner. When Earth was farther away, light had more distance to travel, so we saw events later. By carefully measuring these delays and knowing the distances involved, Rachmer calculated that light traveled at about 220,000 kilometers per second. Not perfectly accurate by modern standards, but remarkably close for 1676. This was the first proof that light had a finite speed, and it came with a profound implication. When you look at Jupiter, you're not seeing it as it is now. You're seeing it as it was in the past, when the light left Jupiter and began its journey to Earth. Depending on where Earth and Jupiter are in their orbits, you might be seeing Jupiter as it was anywhere from 33 to 52 minutes ago. This discovery opened a Pandora's box of questions. If seeing distant objects means seeing into the past, what does that mean for the concept of now? When you look at Jupiter, what is Jupiter doing right now? You can't know. You can only know what it was doing in the past. There is, in principle, no way to observe what Jupiter is doing at this exact instant, because information cannot travel faster than light. Any signal, any observation, any measurement you could possibly make of Jupiter will always show you Jupiter as it was, never as it is. Here's what will blow your mind about this. The same limitation applies to everything. Your friend across the table? You're seeing them as they were a few nanoseconds ago, because light had to travel from them to you. In casual conversation, we act like we're experiencing the same now, but we're not. You experience your now directly through your consciousness, but you experience everyone else's now only after information about them, carried by light, sound, or other signals, has traveled to you. And all those signals are limited by the speed of light. This isn't just a quirk of observation. This is a fundamental limit on causality itself. Imagine you're standing on Earth and a friend is standing on Mars. If you could somehow see your friend in real time, and they suddenly moved you could know about that movement before light from that movement had time to reach you. But that would mean information traveled faster than light, which would violate causality. It would allow effects to precede causes, opening the door to paradoxes and possibly even time travel. The universe doesn't allow this. The speed of light isn't just the speed of light. It's the speed of causality, the maximum speed at which cause can influence effect. Think of it like this. Imagine you're sitting in the center of a perfectly dark room, and someone turns on a light at the wall. The light expands outward as a sphere, traveling at light speed. Until that sphere of light reaches you, you cannot know the light has been turned on. There is no signal, no method, no trick that could inform you faster than that expanding sphere of light. The speed of light creates a boundary around every event in the universe, a boundary that separates what can know about that event from what cannot yet know. This boundary expands outward at light speed, and until it reaches you, the event might as well not have happened from your perspective. This boundary has a name in physics, the light cone. Every event in spacetime has a past light cone, containing all the events that could have influenced it, and a future light cone, containing all the events it could possibly influence. Events outside your light cone are absolutely, completely unreachable by you. They cannot affect you. You cannot affect them. They exist in a kind of causal void relative to you. And here's the really weird part. For events outside your light cone, the concept of before or after becomes meaningless. We'll explore this more deeply soon, but for now, just hold on to this thought. The speed of light doesn't just affect how we see the universe. It affects what we can mean by now. By the 19th century, physicists knew light had a finite speed, but they still thought of it like any other speed. If you're on a train moving 50 miles per hour and you throw a ball forward at 20 miles per hour, the ball moves at 70 miles per hour relative to the ground, right? Simple addition. Scientists assumed light worked the same way. If you were on a spaceship moving at half the speed of light and you shined a flashlight forward, they thought the light would travel at 1.5 times the normal speed of light relative to someone standing still. This assumption seemed so obvious, so intuitively true, that almost no one questioned it. But then came Albert Einstein in 1905, and he destroyed that assumption completely. Einstein realized something radical. The speed of light is the same for everyone, no matter how fast they're moving. If you're standing still and measure the speed of light, you get 299,792,458 meters per second. If you're on a spaceship moving at 99.99% the speed of light and you measure the speed of a light beam, you still get exactly 299,792,458 meters per second. The light doesn't go faster just because you're moving. This seems impossible, but it's been proven experimentally thousands of times. It's one of the most precisely verified facts in all of physics. How can this possibly work? If you're chasing a light beam at nearly the speed of light, why doesn't the light appear to slow down from your perspective? Einstein's answer was shocking. Time itself slows down for you, and space itself contracts for you in exactly the right way to ensure that you always measure light traveling at the same speed. This is special relativity, and it's not a theory about light. It's a theory about the nature of time and space themselves. Time is not absolute. Space is not absolute. The only thing that's absolute is the speed of light, and everything else, including the rate at which time flows and the distances between objects, adjusts to accommodate this cosmic speed limit. Let me give you an analogy to help this sink in. Think of the universe like an enormous spreadsheet where the speed of light is the formula that must always return the same value. When you change one input to the formula, like your velocity, other inputs must automatically adjust to keep the output constant. In the universe, those other inputs are the rate at which time passes for you and the distances you measure. Move faster, and time literally slows down for you relative to someone standing still. Move faster, and distances literally contract in the direction you're moving. These aren't illusions or measurement errors. Time really does pass at different rates depending on how fast you're moving. Length really does contract. These effects are small at everyday speeds, which is why we don't notice them. But at speeds approaching light speed, they become dramatic and impossible to ignore. This brings us to the core question we're exploring. If time passes at different rates for different observers, what does that mean for now? If time is ticking at one rate for you and a different rate for someone moving relative to you, do you even share the same present moment? And the answer Einstein discovered is shocking. No, you don't. Not in any absolute sense. Your now is not the same as someone else's now if you're moving relative to each other. Let that sink in for a moment. The present moment, the thing you think of as this universal instant that everyone shares, doesn't actually exist as a universal instant. It's relative. It's different for different observers. The speed of light doesn't just define how quickly information can travel. It defines the structure of time itself, including what we mean by the present. We'll explore exactly how this works in the next section. But first, take a moment to appreciate how strange this is. Everything you've experienced your entire life has felt like it happened. Now, you've assumed that while you're experiencing this moment, everyone else in the universe is also experiencing this same moment, just in different places. But that's not true. An astronaut on the International Space Station, moving at about 28,000 kilometers per hour relative to you, is experiencing a now that is slightly different from yours. Someone on a planet orbiting a star in another galaxy, moving at a different velocity relative to our galaxy, might have a now that is years different from ours. Events we consider in our future might already be in their past, and events we consider in our past might still be in their future. The speed of light is the cosmic thread that weaves together space and time into a single fabric called spacetime. And once you pull on that thread, the whole tapestry of reality starts to look completely different. But we're just getting started. Everything I've told you so far is just the foundation. The real mind-bending implications are still ahead. If you're already feeling like your brain is being twisted into knots, good. That means you're starting to glimpse the true nature of reality. Hit that subscribe button if you haven't already, because we're about to go much, much deeper. So we've established that the speed of light is finite and constant for all observers, which leads to time dilation and length contraction. But what does this actually mean for the concept of now? To understand this, we need to explore one of the most counterintuitive predictions of Einstein's relativity, the relativity of simultaneity. This is the idea that two events that are simultaneous for one observer happening at the same time might not be simultaneous for another observer moving at a different velocity. In other words, whether two events happen at the same time depends on who's watching. Let me walk you through a thought experiment that Einstein himself used to explain this concept. Imagine you're standing on a train platform and a train is passing by at a very high speed, let's say half the speed of light. On the train, exactly in the middle of one of the cars, someone sets off a light flash. From the perspective of someone on the train, the light expands outward in a sphere, hitting the front and back walls of the train car simultaneously. This makes perfect sense because the light source is equidistant from both walls, and light travels at the same speed in all directions. So of course, it hits both walls at the same time. But now let's think about what you see standing on the platform watching the train go by. You also see the light flash, and you also see the light expanding outward as a sphere at the speed of light. But here's the crucial difference. From your perspective, the train is moving. The back wall of the train is moving toward where the light was emitted, and the front wall is moving away from where the light was emitted. The light still travels at the same speed in all directions relative to you. But because the back wall is moving toward the light and the front wall is moving away from the light hits the back wall first and the front wall second. From your perspective, these two events, light hitting the back wall and light hitting the front wall, are not simultaneous. They happen at different times. So who's right? Does the light hit both walls simultaneously, or does it hit the back wall first? The answer is both. Both observers are correct within their own reference frames. Simultaneity is not absolute, it's relative. Two events that happen at the same time for one observer can happen at different times for another observer, moving at a different velocity. There is no universal now that both observers share. Each observer has their own present moment, and these present moments don't align. Think of it like this. Imagine two musicians playing in perfect sync in one concert hall, hitting their notes at exactly the same instant. Everyone in the hall hears the notes simultaneously. But now imagine someone is driving past the concert hall at high speed. Because sound has a finite speed, and because the listener is moving relative to the musicians, the sound from the two musicians reaches the moving listener at different times, even though the musicians played simultaneously from the perspective of the audience in the hall. Now replace sound with light, and replace the concert hall with the universe, and you start to see the problem. Every observer has their own definition of simultaneous based on their motion through spacetime. This gets even weirder when you consider events that are far apart in space. Imagine two events happening on opposite sides of the galaxy. For you, standing still relative to the galaxy, maybe these events happen at exactly the same time. They're simultaneous in your reference frame. But someone flying past you at high speed in a spaceship would calculate that one event happened before the other. Someone flying in the opposite direction would calculate that the other event happened first. All three of you would be correct within your own reference frames, even though you completely disagree about the order of events. Now, there's an important caveat here. This only applies to events that are space-like separated, meaning they're far enough apart in space that light couldn't travel from one to the other in the time between them. For events that could influence each other events within each other's light cones, all observers agree on their order. If event A causes event B, all observers will agree that A happened before B. The universe preserves causality, even though it doesn't preserve a universal present moment. You can't have a reference frame where the effect happens before the cause. But for events that can't influence each other, events separated by distances too great for light to bridge in the time between them, different observers can disagree about which happened first without violating causality. This has profound implications. When you think about what's happening right now on Mars, you're asking a question that doesn't have a single answer. Different observers moving at different velocities would all calculate different events on Mars as being simultaneous. With your now, your present moment extends across space in a way that depends on your motion. Change your velocity, and you literally change which distant events are happening now from your perspective. The physicist Brian Greene has a wonderful way of illustrating this. Imagine an alien civilization 10 billion light years away. If that alien is sitting still relative to you, the event on their planet that is simultaneous with your now might be the alien eating breakfast. But if that alien starts moving toward Earth, even at a leisurely walking pace, the event on their planet that is simultaneous with your now shifts. It might shift by hundreds of years. Just by the alien standing up and walking, different events in their planet's timeline become simultaneous with your present moment. Walk one direction, and events in their past align with your now. Walk the other direction, and events in their future align with your now. This seems impossible, right? How can the mere act of walking change what events are happening now on a planet 10 billion light years away? The answer is that those events were always happening past, present, and future all exist in the same way. Your motion just changes which slice of spacetime you consider to be the present. We'll explore this idea of the block universe more later, but for now, just absorb this reality. The present moment is not a universal instant that sweeps through the cosmos like a hand across a clock. The present moment is personal, local, defined by your motion through spacetime. Here's another way to think about it. You know how when you look at a three-dimensional object from different angles, you see different two-dimensional cross-sections of it. If you slice a cube perpendicular to one axis, you get a square. Tilt your slice, and you get a rectangle. The cube itself hasn't changed, but your perspective on it has, revealing different cross-sections. Spacetime is like a four-dimensional structure, and your present moment is like a three-dimensional slice through that structure. Different observers moving at different velocities are effectively tilting their slices at different angles through spacetime, revealing different cross-sections as they're now. This is why physicists often say that time is the fourth dimension. It's not just a metaphor. Space and time are woven together into a four-dimensional fabric called spacetime, and your motion through space affects your motion through time. When you move through space, you're rotating your perspective on spacetime, tilting your slice of now to include different events. The man who first fully developed this mathematical picture of spacetime was Hermann Minkowski, Einstein's former mathematics professor. In 1908, Minkowski gave a famous lecture where he declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This was radical. For all of human history, people had thought of space as the stage where events unfold, and time as the progression of those events. Minkowski showed that space and time are not separate. They're two aspects of a single entity, spacetime. In Minkowski's spacetime, every event is a point with four coordinates, 3 for space and 1 for time. Your entire life, from birth to death, is a four-dimensional path through spacetime called your world line. When you're standing still, your world line points straight into the future. You're moving through time, but not through space. When you walk across a room, your world line tilts, now pointing both into the future and in the direction you're walking. You're moving through both time and space simultaneously. Here's the kicker. Nothing is ever standing still in spacetime. Even when you're sitting perfectly still in space, you're still moving through spacetime at the speed of light. Yes, you read that right. You are always moving at the speed of light through spacetime. How? Because your motion through spacetime is divided between motion through space and motion through time. When you're standing still in space, all of your motion is through time. Time is passing at the maximum rate for you. When you start moving through space, some of your motion through spacetime is diverted from the time direction into the space direction. This is why time slows down when you move. You're using up some of your motion through spacetime to move through space, so less is left over for motion through time. Think of it like this. Imagine you're driving north on a highway at 60 miles per hour. All of your velocity is pointed north. Now you turn slightly to the northeast. You're still going 60 miles per hour, but now some of that velocity is pointed east and less is pointed north. Your northward speed decreases because some of your total velocity has been redirected. In spacetime, everyone always moves at light speed, but that motion can be divided between space and time. Move faster through space, and you move slower through time. Photons, particles of light, move through space at light speed, which means they move through time at 0 speed. From a photon's perspective, no time passes at all. It's emitted and absorbed in the same instant, even if it crosses the entire universe. For a photon, the universe has no duration. This is getting abstract, so let me ground it with some real numbers from actual experiments. Scientists have tested time dilation countless times with incredibly precise atomic clocks. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial airliners, some traveling eastward and some westward. When they compared these clocks to identical clocks that stayed on the ground, they found that the traveling clocks had ticked fewer times. They had aged less. The eastward clocks lost about 59 nanoseconds, and the westward clocks gained about 273 nanoseconds compared to the ground clocks. These tiny differences matched Einstein's predictions almost perfectly, accounting for both the speed of the planes and the difference in gravitational field at altitude. Today, we deal with time dilation constantly in GPS satellites. GPS satellites orbit Earth at about 14,000 kilometers per hour and are about 20,000 kilometers above the surface. Because they're moving fast and are in a weaker gravitational field than Earth's surface, time passes at a different rate for them than for us on the ground. The satellite's clocks tick about 38 microseconds faster per day than clocks on Earth's surface. If we didn't correct for this effect, GPS positioning would drift by about 10 kilometers per day, making GPS completely useless. Every time you use Google Maps to navigate, you're relying on corrections for relativistic time dilation. Particle accelerators provide even more dramatic evidence. When particles are accelerated to 99.99%, the speed of light in facilities like the Large Hadron Collider, their internal clocks slow down dramatically. Muons, unstable particles that normally decay in about 2.2 microseconds, can last hundreds of times longer when moving at near light speed because time is passing more slowly for them. From the muon's perspective, time is passing normally, but the laboratory outside is time-lapsed, experiencing time at a faster rate. From the laboratory's perspective, the muon is in slow motion, its internal clock running slow. Both perspectives are correct within their own reference frames. So where does this leave us on the question of whether the present moment is defined by light speed? So far, we've seen that the speed of light is constant for all observers, that this constancy leads to time dilation and the relativity of simultaneity, and that these effects mean there is no universal present moment shared by all observers. Different observers moving at different velocities slice spacetime differently, creating different nows that include different sets of events. But we've only scratched the surface. What we haven't fully explored yet is what this means for the nature of time itself. Does the past still exist? Does the future already exist? If different observers disagree about what's happening now, does that mean all moments exist equally, just from different perspectives? These are the questions that lead us into the block universe, one of the most profound and controversial ideas in modern physics. But before we go there, let me give you a retention hook to carry you forward. What if I told you that the moment of your birth and the moment of your death both exist right now, not as memories or predictions, but as equally real events in spacetime, and that you're just slowly becoming aware of them as your consciousness moves along your world line? Hold that thought, because in the next section, we're going to explore whether time actually flows at all, or whether that flow is an illusion created by the structure of consciousness itself. Before we can fully understand the block universe, and whether all moments of time exist simultaneously, we need to address a question that probably seems obvious, but is actually deeply strange. Why does time have a direction? We call this the arrow of time. You've lived your entire life experiencing time flowing from past to future. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. You remember yesterday, but not tomorrow. These asymmetries seem so fundamental that we rarely question them. But here's the thing. The fundamental laws of physics don't actually distinguish between past and future. If you watch a video of two billiard balls colliding and bouncing apart, you can't tell if the video is playing forward or backward. The collision looks equally plausible in both time directions because Newton's laws of motion work the same way forward and backward in time. The same is true for Einstein's equations, Maxwell's equations for electromagnetism, and even quantum mechanics at the most fundamental level. All of these theories are time symmetric, meaning they work equally well if you run time backward. So why does the universe have a clear arrow of time? Why do we age in one direction? Why do we remember the past but not the future? The answer lies in a concept called entropy, and understanding entropy is crucial to understanding the present moment because entropy is intimately connected to how we perceive time. Entropy is often described as disorder or randomness, but it's more accurate to think of it as the number of ways a system can be arranged microscopically while still looking the same macroscopically. A low entropy state is one with very few possible arrangements. It's highly ordered, special, unlikely. A high entropy state is one with many possible arrangements. It's disordered, generic, likely. And here's the crucial fact. In any isolated system, entropy tends to increase over time. This is the second law of thermodynamics, one of the most ironclad principles in all of physics. Think of it like this. Imagine a deck of cards perfectly sorted by suit and rank. This is a low entropy state because there's only one arrangement that counts as perfectly sorted. Now shuffle the deck once. It's now in a high entropy state because there are billions of possible arrangements that count as shuffled. If you keep shuffling, the deck will stay shuffled. It won't spontaneously return to perfect order because there are so many more ways to be shuffled than to be sorted. That's entropy increasing. The reason eggs don't unbreak and coffee doesn't spontaneously heat up is because these processes would require entropy to decrease, which means going from a generic, likely state to a special, unlikely state. It's not impossible. The atoms in the broken egg could theoretically all bounce back together in exactly the right way to reassemble the egg, but it's so astronomically unlikely that we never see it happen. The universe started in a very low entropy state at the Big Bang, and it's been increasing in entropy ever since, rolling downhill from a special, ordered state toward a generic, disordered state. Here's where this connects to the arrow of time. Our perception of time's flow is intimately tied to the increase in entropy. We remember low entropy states we call the past, and we observe the universe evolving toward higher entropy states we call the future. Our memories are physical records encoded in low entropy configurations in our brains, and the process of forming memories increases entropy. The reason you remember yesterday, but not tomorrow, is fundamentally linked to the second law of thermodynamics. But here's the mind-bending part. If the fundamental laws of physics are time-symmetric, then in principle, every moment of time is equally real. The equations don't care about past, present, or future. They describe a four-dimensional spacetime where all events simply exist, and the concept of flow might be an illusion created by conscious beings whose brains happen to store memories in only one time direction. This brings us to one of the most controversial and profound ideas in physics, the block universe, also called eternalism. In the block universe model, all of spacetime exists as a single, unchanging, four-dimensional structure. The past doesn't no longer exist, and the future doesn't not yet exist. They both exist in exactly the same way the present exists. They're just located at different coordinates in the time dimension, just as Paris and Tokyo both exist even though they're at different coordinates in space. Think of spacetime as a giant loaf of bread. Each slice of bread represents a different moment in time. One slice is yesterday, one is today, one is tomorrow. From the perspective of the loaf as a whole, all the slices exist simultaneously. The entire loaf is the block universe, containing all of past, present, and future. Your consciousness is like a moving spotlight that illuminates one slice at a time, creating the subjective experience of now moving through time. But the spotlight doesn't create the slices or make them real. It just illuminates them. All the slices exist, whether you're experiencing them or not. This might sound like philosophical speculation, but many physicists take the block universe seriously because it emerges naturally from relativity. Remember the relativity of simultaneity? If different observers moving at different velocities have different definitions of now, and if these definitions are all equally valid, then it's hard to argue that only one particular now is real. If your now includes events that are in my past or my future, and my now includes events that are in your past or your future, how can we say that only one of these nows truly exists while the others are merely memories or possibilities? The physicist and philosopher Hilary Putnam put forward a famous argument for the block universe based on this reasoning. He argued that if two observers can have different sets of events in their present moment, and both observers' present moments are equally real, then all events they both consider present must be equally real. But by changing velocities, observers can shift their present moments to include essentially any event in the history of the universe, past or future. Therefore, all events must be equally real. Past, present, and future all exist. This is sometimes called Putnam's argument for the reality of all times. And while it has been debated and refined over the decades, its core insight remains powerful. Relativity seems to force us to accept that all moments of time have the same ontological status. They all exist in spacetime. We just happen to be experiencing them sequentially. Now, I know what you're thinking. If the future already exists, does that mean it's predetermined? Do we have no free will? Are our choices meaningless? These are deep questions that we'll explore more later. But for now, let me say this. Even in a block universe, your choices are real and meaningful. The future exists in the block, but it exists as a future shaped by the choices you make. Think of it like this. Right now, you're reading this script. In the block universe, this event you reading these words at this moment exists as a point in spacetime. 2 minutes from now, another point in spacetime exists where you finished this section. Both points exist in the block. But the second point includes the consequences of choices you made in the first point. The block doesn't eliminate causality or choice. It just says that all the moments of time containing those causes and choices and consequences all exist together in spacetime. Let me introduce you to a physicist whose work is central to this discussion, Julian Barbour. Barbour has spent decades developing a radical theory of time based on the block universe concept. In his view, time doesn't exist at all as a fundamental feature of the universe. Instead, what we call time is an emergent phenomenon arising from the configuration of matter and energy in the universe. Each moment is a complete, self-contained configuration of the universe that Barbour calls a now. All these nows exist simultaneously in what he calls Platonia, a space of all possible configurations. The appearance of time flowing is an illusion created by correlations between these nows. Each now contains records and memories that seem to point to previous nows, creating the illusion of a sequence, even though no sequence actually exists fundamentally. Barbour's theory is controversial and not universally accepted, but it takes seriously the implications of relativity and quantum mechanics. If there's no universal present moment, Barbour argues, then there's no universal time. What we experience as time is just the fact that our consciousness is embedded in a particular now that contains memories of other nows. This might sound crazy, but similar ideas appear in quantum mechanics, which is our best theory of how the universe works at the smallest scales. In quantum mechanics, the universe exists as a superposition of all possible states until the measurement is made. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that all possible outcomes of quantum events actually occur, branching into parallel universes. In this view, the block contains not just all moments of time, but all possible histories of the universe. Here's where the speed of light comes back into the picture in a crucial way. The block universe isn't just a static four-dimensional structure. It has a geometry defined by the speed of light. Remember light cones? Every event has a past light cone containing all the events that could have influenced it, and a future light cone containing all the events it could influence. The structure of these light cones defined by the speed of light is what gives space-time its shape and determines which events can be causally connected. In the block universe, causality isn't about the past affecting the future. Those are human concepts tied to our subjective experience of time. Instead, causality is about the geometric structure of spacetime. Events inside each other's light cones can be causally related. Events outside each other's light cones cannot. The speed of light defines the boundaries of causal influence, which in turn defines the structure of the block. Without the finite speed of light, the geometry of spacetime would be completely different, and the notion of causality would change radically. Here's an analogy. Imagine a city where the speed limit is how fast information can travel. This speed limit determines which neighborhoods can communicate with which other neighborhoods within a certain time. The shape of the city, which parts are close, which are far, which are connected, is defined by this speed limit. Similarly, the speed of light determines the shape of spacetime, defining which events are close or far, connected or disconnected, able to influence each other or isolated. Now, let's connect this to your direct experience. When you look at a star in the night sky, you're seeing light that left that star years, decades, or even thousands of years ago. That light has been traveling through the block of spacetime, moving along a path called a null geodesic, a trajectory that light always follows through spacetime. When that light reaches your eye, it's creating a causal connection between an event in the star's past and an event in your present. The light cone from that distant event has expanded across spacetime and intersected with your world line, allowing you to observe an event that happened long ago. But here's the truly weird implication. In the block universe, that distant event didn't happen long ago and then ceased to exist. It still exists, just like your present moment exists. The star emitting that light is not gone. It's simply located at different coordinates in spacetime than you are. When you see the star, you're not seeing a ghost of something that used to exist. You're seeing an event that exists in spacetime, just not at the same time coordinate as your present experience. This reframes everything. You're not a being moving through time, watching the past disappear and the future arrive. You're a four-dimensional object extended through spacetime, and your consciousness is experiencing different slices of that four-dimensional object sequentially. Every moment of your life, from your first breath to your last, exists as part of your world line in spacetime. Your birth exists. Your childhood exists. This moment exists. Your future exists. They're all equally real, just located at different points along the time dimension. The speed of light is what prevents you from experiencing all these moments simultaneously. Because information can only travel at light speed, and because your consciousness relies on information processing in your brain, you can only be aware of a limited slice of spacetime at any given moment. The speed of light creates a kind of horizon around your present experience, limiting what you can know and perceive. It's like you're walking through a dark building with a flashlight that only illuminates a small area around you. The entire building exists, but you can only see the part illuminated by your light. Similarly, all of spacetime exists, but you can only experience the slice illuminated by your present consciousness. If this is making your brain hurt, good. You're grappling with ideas that challenge the deepest intuitions we have about reality. And we're not done yet. We still need to explore how this understanding affects concepts like free will, identity, and meaning. But right now, I want you to pause and really absorb what we've covered. The present moment as you experience, it is not a universal, now shared by everyone in the cosmos. It's a personal slice of spacetime, defined by your motion and your position. The flow of time from past to future might be an illusion created by entropy and consciousness. And all moments of time past, present, and future might exist simultaneously in a four-dimensional block of spacetime whose structure is defined by the speed of light. Before we move on, make sure you've hit that like button and subscribed, because we're about to dive even deeper into the implications of all this. In the next section, we're going to explore the concept of your personal present moment in more detail, examining how your brain constructs the experience of now, and why that experience might be fundamentally different from the physical reality of spacetime. What you think of as the present is already the past by the time you experience it, and that's going to lead us into some truly mind-bending territory about consciousness itself. Stay with me. Let's talk about your personal experience of the present moment, because it's not what you think it is. You have this feeling that you're experiencing the present in real time, that your consciousness is aligned with now as events happen. But this is an illusion constructed by your brain, and understanding this illusion will help us see even more clearly how the speed of light defines what we call the present. When you clap your hands, you feel like you hear the clap at the same moment you feel your hands making contact. But that's not what's happening. Sound travels at about 343 meters per second in air, vastly slower than light. The sound of the clap has to travel from your hands to your ears, and then the signal has to travel from your ears to your auditory cortex via electrical impulses in your neurons, which travel at speeds ranging from about 1 to 100 meters per second, depending on the type of neuron. Meanwhile, the sensation of touch travels from the nerves in your hands to your somatosensory cortex at similar speeds. These signals are taking different amounts of time to reach different parts of your brain, yet you experience them as simultaneous. How does your brain pull this off? The answer is that your brain actively constructs the experience of simultaneity by adjusting the timing of different sensory inputs. Your brain knows how long it typically takes for signals to arrive from different senses and different parts of your body, and it holds on to faster signals briefly to allow slower signals to catch up, creating an artificially synchronized experience of now. This is called temporal binding, and it means that what you experience as the present moment is actually a carefully edited compilation of events that happened at slightly different times in the physical world. Neuroscientist David Eagleman has done fascinating research on this. He conducted experiments where people wear prism glasses that shift their visual field to one side. At first, when they try to reach for an object, they miss because their visual perception doesn't match the location of their hand. But after wearing the glasses for a while, their brain adapts, recalibrating the timing and interpretation of visual and motor signals so that everything feels synchronized again. The brain is constantly adjusting what you perceive as now to create a coherent experience. But it gets weirder. The present moment you experience is not just synchronized, it's also delayed. There's a processing time between when light from the world enters your eye and when you become consciously aware of what you're seeing. This delay is typically about 80 to 100 milliseconds, about a tenth of a second. That means everything you're consciously experiencing right now actually happened a tenth of a second ago. You're living in the past, always, even in your own reference frame. Think about that for a moment. The words you're reading on this screen right now, you're actually seeing them as they were about 100 milliseconds ago. The light bounced off the screen, traveled to your eye in a few nanoseconds. The signal was processed through your retina and optic nerve, traveled to your visual cortex, was processed through multiple layers of neural networks, and only then did you become consciously aware of the words. By the time you're aware of something, it's already in the past. This delay isn't a bug, it's a feature. Your brain uses this processing time to construct a stable, coherent representation of the world. The raw sensory data coming into your brain is noisy, fragmented, and ambiguous. Your brain has to interpret this data, fill in gaps, correct errors, and integrate information from multiple senses. All of this takes time. The present moment you experience is not reality as it is right now. It's your brain's best guess at reality based on slightly outdated information. There's a famous experiment that demonstrates this, called the flash lag effect. If you flash a stationary object, at the same time a moving object passes by it, the moving object appears to be ahead of the stationary object, even though they were perfectly aligned when the flash occurred. Your brain is predicting where the moving object will be by the time you become conscious of it, and it shifts your perception accordingly. You're not seeing where things are. You're seeing where your brain predicts they'll be by the time you process the visual information. Professional athletes rely on this predictive processing. A baseball batter has about 400 milliseconds from when a pitch is thrown to when it crosses the plate. Given that conscious visual processing takes about 100 milliseconds, the batter can't consciously react to the ball's trajectory in real time. Instead, the brain has to predict the ball's path based on early visual cues and initiate the swing before, consciously perceiving where the ball will be. Top batters aren't consciously seeing the ball and hitting it. Their brains are predicting its trajectory and acting on that prediction. This means that your experience of the present is partly a prediction of the near future. Your brain is constantly running slightly ahead, trying to compensate for its own processing delays by forecasting what will happen next. The now you experience is a hybrid of delayed perception and predictive simulation. Here's how this connects back to the speed of light and relativity. We've been talking about how the speed of light creates delays in observing distant events, but now we see that even local events, things happening right in front of you, are perceived with delays due to neural processing. There are actually multiple layers of delay between an event and your conscious experience of it. First, the time for light to travel from the event to your eye. Second, the time for neural signals to travel from your eye to your brain. Third, the time for your brain to process and integrate that information into conscious awareness. This raises a philosophical question. If the present moment you experience is constructed by your brain from delayed and predicted information, is there any meaningful sense in which you experience the actual present? Or are you always living in a mentally constructed simulation that's slightly out of sync with physical reality? Let me introduce you to the concept of specious present, a term coined by philosopher and psychologist E. Robert Kelly and later developed by William James. The specious present is the duration of time that you experience as now. If I ask you what's happening now, you don't just perceive a single instant, you perceive a short window of time, maybe a few seconds long, as if it's all happening at once. When you listen to music, you don't hear each note in isolation. You hear melodies, which require experiencing multiple notes as part of a cohesive now. When someone speaks to you, you don't hear isolated phonemes. You hear words and even whole sentences as units that feel present to you. Experiments suggest that the specious present lasts somewhere between 2 and 3 seconds for most people. This is the window of time that your brain integrates into a single experience of now. Events within this window feel immediate and present. Events outside this window feel like the past or the future. But this window is entirely constructed by your brain. There's no 2 to 3 second window in the physical structure of spacetime. It's a feature of consciousness, not a feature of the universe. Different aspects of consciousness have different integration windows. Your perception of visual motion integrates information over about 100 to 150 milliseconds. Your perception of rhythm in music can integrate over several seconds. Your sense of self and autobiographical continuity integrates information over much longer periods, possibly minutes to hours to a lifetime. This means that the present moment is not a single well-defined thing, even in your own subjective experience. It's a nested hierarchy of integration windows at different timescales, all contributing to your sense of now. At the shortest timescales, individual neurons fire and integrate signals over milliseconds. At longer timescales, neural networks synchronize and create perceptual experiences over tens to hundreds of milliseconds. At even longer timescales, you experience thoughts, emotions, and intentions that unfold over seconds to minutes. And at the longest timescales, you have memories, goals, and a sense of identity that spans years. Here's where things get really strange. Experiments on timing and conscious awareness have revealed something called backward referral in time. This was discovered by neuroscientist Benjamin Libet in the 1970s. Libet found that when a stimulus is presented, the brain activity associated with consciously perceiving the stimulus doesn't peak until about 500 milliseconds later. But subjects report perceiving the stimulus as if it happened at the time of the stimulus, not half a second later. It's as if the brain is retroactively assigning the conscious experience to an earlier moment in time, making you feel like you perceived something when it happened, even though the neural correlates of that perception occurred much later. This suggests that your brain doesn't just delay and predict. It also edits the timeline of your experience, assigning conscious experiences to moments in time that fit a coherent narrative. even if the underlying neural events happened at different times. Your experience of time is literally constructed and edited, like a film that's been cut and spliced to create a smooth narrative. Now think about how all of this interacts with the relativistic effects we discussed earlier. Not only is there no universal present moment shared by all observers in spacetime, but even within a single observer, there's no single, clear-cut present moment. Your brain is synthesizing information from multiple sources with different delays, integrating it over multiple timescales, predicting the future, and retroactively editing the timeline of your experience. The present moment is a multi-layered construction happening in your consciousness, built on top of a physical reality where simultaneity is relative and the speed of light imposes fundamental limits on information. What you call now is a narrative your brain tells you, a story stitched together from fragments of the past, predictions of the future, and a constant stream of delayed sensory information, all synthesized into a coherent experience that feels like it's happening in real time. But it's not real time. It's a time-delayed, edited, predicted simulation running in your brain. Let me give you a concrete example to tie this all together. Imagine you're watching a lightning storm. You see a flash of lightning, and then, a few seconds later, you hear the thunder. Your brain knows that lightning and thunder are caused by the same event, so it doesn't feel like two separate things happening at different times. Instead, your brain constructs the experience of a single event, the lightning strike, that has visual and auditory components, even though those components reached you at different times. But now think about what's really happening at multiple levels. The lightning strike happens, releasing light and creating a shockwave. The light travels to your eye at 300,000 kilometers per second and arrives in a few microseconds. The sound travels at 343 meters per second and takes several seconds to arrive. Already, there's a massive difference in arrival times. Then the light signal is processed through your visual system over about 100 milliseconds, while the sound is processed through your auditory system over a similar time frame. Then your brain integrates these two signals into a single experience of the lightning strike, even though they arrived seconds apart. But it doesn't stop there. From the perspective of relativity, if someone else is moving relative to you at high speed, they would disagree with you about the exact moment when the lightning strike occurred. Their now, when the lightning struck, is different from your now. And if we're being precise, the light from the lightning that reaches you left the lightning bolt a few microseconds ago. So you're seeing the lightning as it was in the past, not as it is now. Meanwhile, your conscious experience of seeing the lightning is happening 100 milliseconds after the light entered your eye. So you're becoming aware of an event that happened 100 milliseconds plus a few microseconds ago. Every layer of analysis reveals another layer of delay, another layer of relativity, another way in which the present moment is not a simple, immediate, universal thing. The present moment is defined and constrained at every level by the speed of light, both the cosmic speed limit of light traveling through spacetime and the much slower speeds at which signals travel through neurons in your brain. Here's the profound implication. Your personal now is a construct that exists nowhere else in the universe. No one else experiences the exact same present moment you do, because no one else has your exact motion through spacetime, your exact position, and your exact neural processing. Your present moment is unique to you. It's defined by the speed of light, limiting how quickly information can reach you from the outside world, and by the speed of neural transmission, limiting how quickly your brain can process that information. This has some beautiful philosophical implications. The present moment is not something you passively receive from the universe. It's something you actively create through the act of being conscious and processing information. The universe provides raw events scattered across spacetime, and your consciousness weaves those events into a tapestry of experience that you call now. Does this mean the present moment is entirely subjective? In one sense, yes. Your experience of the present is constructed by your brain and is unique to you. But in another sense, no. The construction is constrained by objective physical facts, the speed of light, the laws of relativity, the structure of spacetime, the architecture of your brain. Your brain can't construct just any present moment. It has to construct a present moment that's consistent with the information it receives, and that information is limited and shaped by the speed of light. Think of it like this. The present moment is like a painting. The canvas and paints are provided by the objective physical universe spacetime, the speed of light, the laws of physics. But the painting itself, the specific experience of now, is created by the artist, which in this case is your consciousness. Different artists, different conscious observers, will create different paintings, different experiences of the present, even when working with the same materials. This brings us to another retention hook. If your present moment is a construction unique to you, does that mean you're isolated, trapped in your own subjective now? Or is there a way to share the present with others? We talk about being present with people, about living in the moment together. Is that possible if everyone has their own separate present? And what does all of this mean for the connection between consciousness and time? Is consciousness itself an emergent phenomenon tied to the arrow of time and the increase of entropy? Could there be conscious beings who experience time differently than we do, or even beings who experience all of time simultaneously? These are the questions we'll explore next, but before we get there, take a moment to reflect on this. Every moment of connection you've ever felt with another person, every shared experience, every "we're in this together" feeling, all of it happened across the unbridgeable gap between your personal now and theirs. And yet, those connections felt real. That should tell you something profound about the nature of consciousness and reality. We'll unpack what exactly that is in just a moment. We've spent a lot of time breaking down the present moment, showing how it's relative, constructed, delayed, and unique to each observer. But now I want to zoom out and address a question that's probably been nagging at you. If all of this is true, how do we ever connect with other people? How do we share experiences? When you watch a sunset with someone you love, are you really experiencing it together? Or are you each trapped in your own separate, relativistically distinct present moment? This is where we need to talk about the concept of causal connection and how it relates to the shared human experience of time. While it's true that the absolute present is relative and different observers disagree about simultaneity, there's a deeper sense in which people can share a present through causal connection and information exchange. Think about a conversation. When someone speaks to you, sound waves travel from their mouth to your ear at 343 meters per second. If you're standing 2 meters apart, the sound takes about 6 milliseconds to reach you. Add another 100 milliseconds for your brain to process what you heard, and you're perceiving their words about 106 milliseconds after they spoke them. Meanwhile, they're seeing your reaction to their words with a similar delay. Every conversation is actually a sequence of causally connected events unfolding with these tiny delays. But the delays are so small relative to human perception that we experience the conversation as immediate and shared. What makes this work is that even though you're not experiencing the same absolute moment, you're within each other's light cones. The events you're experiencing can causally affect each other. Their speaking causes your hearing. Your response causes their hearing. This creates a chain of causality that links your experiences together into what feels like a shared present. Even though strictly speaking, you're each experiencing slightly different moments. The key insight is that sharing a present doesn't require experiencing the exact same absolute time coordinate. It requires being causally connected, being able to influence each other and respond to each other within a time frame short enough that the delays don't matter for the interaction. For humans separated by normal distances, the speed of light delays are utterly negligible. Even if you're video calling someone on the other side of Earth, the signal only takes about 67 milliseconds to travel through fiber optic cables around the planet, well within the window of normal human interaction. It's only when we think about truly vast distances that the relativity of simultaneity and the finite speed of light start to break our intuitive notion of sharing a present. If you're talking to someone on Mars via radio, there's a delay of 3 to 22 minutes depending on orbital positions. At that point, you're not having a conversation in any normal sense. You're exchanging messages with someone who is, from your perspective, living in the past. By the time you receive their message and respond, they've moved on. You're no longer causally connected in a way that creates a shared present. Instead, you're sending information across a gap in spacetime. But for everyday human interactions on Earth, the relativistic effects are tiny enough that we can, for practical purposes, talk about a shared present without being too wrong. The relativity of simultaneity between two people walking at different speeds is measured in nanoseconds or picoseconds, utterly insignificant compared to the second-to-second flow of conscious experience. This is why relativity felt like such an abstract theory for so long. Its effects don't show up in daily life because the speeds we move at and the distances we cover are so small compared to the speed of light. However, there's a deeper way to think about shared experience that doesn't depend on simultaneity at all. When you and a friend watch a movie together, you're not experiencing the same absolute moment. Your brains are processing the sensory information with slightly different delays. Your attention is wandering to different details. Your internal states are different. Yet you'd both say you watched the movie together, and that shared experience is real and meaningful. Why? Because your experiences are correlated. You both saw the same images, heard the same sounds, and can later discuss those stimuli with each other. The correlation between your experiences creates a shared reality, even though the experiences themselves were subjective and asynchronous. This is true of all shared human experiences. When we say we're experiencing something together, we don't mean our subjective presence are perfectly aligned in some absolute sense. We mean our experiences are correlated, causally connected, and mutually accessible through communication. The shared present is less about occupying the same moment in time and more about occupying the same causal structure in spacetime, being close enough that we can interact, influence each other, and build correlated memories. In the block universe view, this becomes even clearer. Your world line and your friend's world line are two paths through spacetime. And wherever those paths are close together in space and overlapping in time, there's the possibility for causal interaction. The segments of your world lines where you're having a conversation are intertwined in spacetime, sending light and sound back and forth, creating a web of causal connections. That web of connections is the shared experience, and it exists in the four-dimensional structure of spacetime, regardless of how you slice up time into moments. Now let's take this idea further and explore how consciousness itself might be related to time and the speed of light. We've talked about how your brain constructs the present moment, but we haven't really addressed the hard problem of consciousness. Why is there subjective experience at all? Why does it feel like something to be you? This is one of the deepest mysteries in science and philosophy, and I'm not going to claim we have a complete answer. But there are some fascinating ideas about how consciousness might be fundamentally tied to time, entropy, and information processing, all of which connect back to the speed of light. One idea, proposed by neuroscientist and cognitive scientist Anil Seth, is that consciousness is a kind of controlled hallucination. Your brain is constantly generating predictions about what it expects to perceive based on its model of the world, and it compares those predictions to incoming sensory data. The experience of consciousness, what it feels like to see, hear, think, and feel, is the process of your brain updating its predictions based on prediction errors. In this view, consciousness is fundamentally about processing information, updating models, and minimizing surprise. But information processing takes time. It requires signals to travel, computations to run, and states to change. The speed at which neurons transmit signals and the speed at which neural networks can update their states impose limits on how quickly consciousness can operate. There's a minimum timescale for conscious experience, determined by the biophysics of neurons. This is why your specious present has a duration your brain needs time to integrate information into a coherent experience. Here's where it gets fascinating. If consciousness is fundamentally about information processing, and information is constrained by the speed of light, then in a deep sense, the speed of light constrains consciousness itself. You can't be conscious of things faster than your brain can process information about them. And information processing is ultimately limited by how fast signals can travel. Now, what if we imagine a consciousness that works differently? What if there were a being whose neurons transmitted signals at the speed of light, or whose information processing happened through photons rather than electrochemical signals? Such a being would experience time very differently from us. Events we perceive as simultaneous might seem spread out to them. Events we see as sequential might seem simultaneous to them. Their specious present might be vastly shorter than ours, allowing them to perceive fluctuations and changes we can't even detect. Conversely, imagine a consciousness much slower than ours, perhaps based on chemical diffusion or mechanical processes. For such a being, what we experience as a brief moment might stretch into hours or days. A conversation with a human might take years from their perspective. The speed of light would still be the ultimate limit, but their conscious experience would be operating on a much slower timescale within that limit. This thought experiment reveals something important. The experience of the present moment is not just about the objective structure of spacetime. It's also about the timescale on which a conscious system operates. Different conscious systems could carve up spacetime into different presents, not just because of their motion through spacetime, relativity, but because of the rate at which they process information, neuroscience, and computation. There's also a connection here to entropy and the arrow of time. Remember, we perceive time flowing from past to future because entropy increases in that direction. Our memories are records of lower entropy past states, and we can't remember higher entropy future states. But consciousness itself might be fundamentally tied to the entropy gradient. Physicist Sean Carroll has written extensively about this. He argues that the arrow of time, the directionality from past to future, is essential for consciousness because consciousness requires memory, and memory requires a distinction between past and future. A universe with no entropy gradient, where time has no arrow, might not support consciousness at all because there would be no way to form memories or distinguish what has happened from what will happen. If Carroll is right, then consciousness doesn't just perceive the arrow of time. Consciousness depends on it. And since the arrow of time is defined by the increase in entropy, which in turn is related to the second law of thermodynamics, in the low entropy initial state of the universe, at the Big Bang, consciousness is ultimately a consequence of cosmology. The fact that you're experiencing this moment right now is a result of the Big Bang creating a universe with low initial entropy that's been increasing ever since. And where does the speed of light fit into this? The speed of light defines the structure of spacetime in which entropy increases. It determines what can influence what, which regions of spacetime are causally connected, and how information and energy spread through the universe. Without the finite speed of light, the causal structure of spacetime would be completely different. Entropy would behave differently, and consciousness, if it could exist at all, would be nothing like what we experience. Let me bring this back down to earth with a personal story. I remember once sitting on a beach at sunset, watching the sun dip below the horizon. I knew, intellectually, that the sun had actually set about 8 minutes earlier, and I was seeing the delayed image of the sun as it was 8 minutes in the past. But I also knew that the processing in my brain meant I was seeing that delayed image after an additional 100 milliseconds of neural delay. And I knew that my experience of now was spread out over a specious present of a few seconds, integrating the continuously changing light and color of the sky. But none of that intellectual knowledge diminished the experience. The sunset was beautiful. It felt immediate and present. I felt connected to the moment, connected to the place, connected to the cosmos. And I realized that even though the present moment is relative, constructed, and delayed, it's still the only moment I can ever experience. This moment right now, however illusory or subjective or constructed it might be, is all I have. And in a strange way, understanding the physics of time makes those moments more precious, not less. Because if the block universe is right, and all moments of time exist equally, then this moment, this specific configuration of matter and energy and consciousness, that is you reading these words right now, exists forever in space-time. It's not going to disappear when the present moment moves on. It's permanently part of the structure of reality. You, right now, are eternal. That's a lot to take in, so let me give you another retention hook before we move to the next section. We've explored how consciousness creates the present and how the present is tied to entropy and information processing. But there's another angle we haven't fully explored yet: quantum mechanics. So far, we've mostly talked about relativity, but quantum mechanics has its own strange relationship with time and the present moment. In quantum mechanics, the past isn't fixed. The future can influence the present. An observation seems to collapse multiple possible presents into one actual present. How does that fit with everything we've discussed? And does quantum mechanics require a universal present moment, contradicting relativity? These questions lead us into some of the deepest mysteries in modern physics: the conflict between relativity and quantum mechanics, and the search for a theory of quantum gravity that might finally tell us what time really is. That's where we're heading next, and trust me, it gets even weirder from here. Let's dive into quantum mechanics and see how it relates to time and the present moment. If you thought relativity was weird, quantum mechanics is going to scramble your brain in entirely new ways. In relativity, we learned that time is relative, that simultaneity depends on your motion, and that the present moment is not universal. But at least in relativity, events have definite outcomes. If a coin flip happens on the other side of the galaxy, the coin has definitely landed on heads or tails, even if you won't know which one for millions of years until light from that event reaches you. Quantum mechanics says no, that's not how it works. According to quantum mechanics, until you observe the coin, it doesn't have a definite outcome. It exists in a superposition of both heads and tails simultaneously, and only when you measure it does it collapse into one outcome or the other. The act of observation seems to play a fundamental role in determining what happens, which raises a huge question. What counts as an observation? And when, exactly, does this collapse happen? Is there a definite present moment when the quantum state collapses and reality becomes fixed? Let me introduce you to one of the most famous thought experiments in physics: Schrodinger's cat. Erwin Schrödinger proposed this in 1935 to highlight how absurd quantum mechanics seems when applied to everyday objects. Imagine a cat in a sealed box with a vial of poison, a radioactive atom, and a Geiger counter. If the atom decays, the Geiger counter detects it and breaks the vial, killing the cat. If the atom doesn't decay, the cat lives. According to quantum mechanics, before you open the box, the atom exists in a superposition of decayed and not decayed. This means the whole system, the Geiger counter, the vial, and the cat, exists in a superposition of cat dead and cat alive. The cat is simultaneously alive and dead until you open the box and observe it, at which point the superposition collapses and the cat becomes definitely alive or definitely dead. This seems crazy. A cat can't be both alive and dead at the same time. But quantum mechanics has been tested in countless experiments, and superposition is real. Electrons can be in two places at once. Photons can have multiple polarizations simultaneously. The equations of quantum mechanics describe superpositions, and these superpositions create interference patterns that we can observe. The question is, why don't we see superpositions in everyday life? Why don't cats exist in superpositions of alive and dead? One answer is decoherence. When a quantum system interacts with its environment, the superposition becomes entangled with the environment in such a complex way that the system appears to collapse into one state or another for all practical purposes. The larger and more complex the system, the faster decoherence happens. For a single electron, you can maintain a superposition for seconds or even minutes with the right equipment. For a cat, decoherence would happen almost instantly, long before you could open the box. This is why quantum weirdness is mostly confined to the microscopic world-larger objects that cohere too quickly to show quantum behavior. But decoherence doesn't fully solve the measurement problem. It explains why we don't see superpositions in practice, but it doesn't explain whether the cat has a definite state before we look, or whether our observation literally creates the definite state. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, which was the dominant view for much of the 20th century, the active measurement collapses the wave function, causing the superposition to become a definite outcome. This seems to require a special role for observation and possibly consciousness, which leads to all sorts of philosophical problems. What counts as an observation? Does a measuring device count, or does it have to be a conscious observer? If observation causes collapse, does that mean reality depends on being observed? In the many worlds interpretation proposed by Hugh Everett in 1957, there is no collapse. Instead, every possible outcome happens in a different branch of reality. When you open the box, the universe splits into one branch where the cat is alive and one branch where the cat is dead. You, the observer, also split one copy of you sees a live cat and another copy sees a dead cat. Both outcomes are equally real. They just exist in different branches of the multiverse. In this view, the wave function never collapses. Superpositions are real and permanent. We just experience one branch of the superposition because we're part of the quantum system ourselves. There are other interpretations to pilot wave theory, where particles have definite positions guided by a quantum wave. Objective collapse theories, where the wave function collapses spontaneously without observation. And more. The point is that quantum mechanics gives us the math to predict experimental outcomes with incredible precision, but it doesn't give us a clear picture of what's actually happening at a fundamental level. Here's how this relates to time and the present moment. In the Copenhagen interpretation, with wave function collapse, there's a sense in which quantum mechanics requires something like a universal present, the moment of collapse when the superposition becomes a definite outcome. This seems to conflict with relativity, where there's no universal present. Different observers moving at different velocities should disagree about when the collapse happens, but quantum mechanics seems to require a definite moment of collapse. Physicist John Bell explored this problem extensively. He showed that quantum mechanics predicts correlations between distant particles called entanglement that can't be explained by any local hidden variable theory. When two particles are entangled, measuring one particle instantaneously affects the state of the other particle, no matter how far apart they are. Einstein famously called this spooky action at a distance, and thought it proved quantum mechanics was incomplete. But experiments have confirmed that entanglement is real. Here's the kicker. When you measure one entangled particle, and it collapses into a definite state, the other particle's state also becomes definite instantaneously. Faster than light could travel between them. This seems to violate relativity, which says nothing can travel faster than light, including information. The resolution is that while the correlation is instantaneous, you can't use it to send information faster than light because the outcome of each measurement is random. You can't control what result you get when you measure your particle, so you can't encode a message in the results. When you later compare results with the person measuring the other particle, which requires sending information at or below the speed of light, you find the correlation, but the correlation was established through quantum entanglement, not through any faster-than-light signal. But this still leaves a puzzle about the present moment. If measuring one particle collapses the wave function of a distant entangled particle instantaneously, there must be some sense in which the collapse happens at a definite moment in time, not a relative moment. Different observers moving at different velocities would disagree about when instantaneously is. This suggests that quantum mechanics and relativity might be fundamentally incompatible in their descriptions of time. Physicist Nicholas Gisin has studied this problem and argues that quantum mechanics requires a preferred frame of reference, a universal present moment in which wave function collapse happens. This would mean relativity's claim that there's no preferred reference frame is wrong, at least when quantum mechanics is involved. But this is highly controversial, and most physicists think there must be a way to reconcile quantum mechanics and relativity without abandoning the core insights of either theory. The most promising approach is quantum field theory, which combines quantum mechanics and special relativity into a single framework. In quantum field theory, particles are excitations of underlying fields that permeate all of spacetime. The fields themselves are quantum, existing in superpositions and exhibiting entanglement, but they obey relativistic rules. Quantum field theory is the framework behind the standard model of particle physics, and it's been incredibly successful at predicting experimental results. But quantum field theory still doesn't include gravity. Relativity says gravity is the curvature of spacetime, which means spacetime itself is dynamic. It bends and warps in response to matter and energy. Quantum mechanics says everything is quantized, existing in discrete chunks. So if spacetime is dynamic and quantum, shouldn't spacetime itself be quantized? Shouldn't there be a quantum theory of gravity? This is the holy grail of modern physics, a theory of quantum gravity that unifies quantum mechanics and general relativity. We don't have such a theory yet, at least not a complete and experimentally verified one. But there are candidates, and they all have radical implications for the nature of time and the present moment. String theory, one of the leading candidates, proposes that the fundamental constituents of reality are not particles, but tiny vibrating strings. Different vibration patterns of these strings correspond to different particles. String theory requires extra dimensions of space beyond the three we experience, and it predicts that spacetime itself is an emergent phenomenon arising from more fundamental quantum processes. In some versions of string theory, time as we know it doesn't exist at the most fundamental level. What we call time is an emergent property that only appears at larger scales, much like temperature is an emergent property of molecular motion. Loop quantum gravity, another approach, quantizes spacetime directly. It proposes that space is made of discrete chunks called loops, connected in a network that forms the fabric of spacetime. In loop quantum gravity, time is also emergent, arising from the dynamics of this network. At the smallest scales, the Planck scale, about 10 to 35 meters, and y-43 seconds spacetime is granular, not smooth, and the concept of a continuous flow of time breaks down. If time is emergent, what does that mean for the present moment? It means that at the most fundamental level, there might not be a present moment at all. The concept of now would be like the concept of temperature, real and meaningful at the macroscopic level, but not fundamental. Just as temperature is the average kinetic energy of many molecules, time might be a statistical or emergent property of many quantum processes. Julian Barber, whom I mentioned earlier, has developed a version of this idea called timeless physics. Barber argues that the fundamental laws of the universe don't refer to time. Instead, they describe relationships between configurations of matter and energy. What we perceive as time is the correlation between these configurations. Each configuration contains records that point to other configurations, creating the illusion of a sequence, even though all configurations exist timelessly in Barber's Platonia. Carlo Rovelli, a physicist who has worked extensively on loop quantum gravity and the nature of time, puts it beautifully in his book, The Order of Time. Rovelli argues that time is not a single thing, but a complex layering of different phenomena: a thermal time arising from entropy, relational time arising from change, and psychological time arising from consciousness. At the deepest level, the fundamental laws of physics might not involve time at all. Time, in all its aspects, is emergent. If this is true, then asking what is the present moment is like asking what is the temperature of a single atom. It's a category error. The present moment is a concept that applies to conscious beings embedded in a thermodynamic system with increasing entropy, not a fundamental feature of reality. But here's the beautiful paradox. Even if time is emergent and the present moment is not fundamental, it's still real for you. Your experience of now, your sense of time flowing, your memories of the past, and plans for the future, all of this is real at the level where you exist and operate. Emergence doesn't make things less real. It just means they arise from simpler underlying processes. Water is just H2O molecules, but that doesn't make wetness any less real when you jump in a pool. Temperature is just average molecular motion, but that doesn't make heat any less real when you touch a hot stove. And time might be just an emergent feature of quantum processes and thermodynamics, but that doesn't make the present moment any less real when you're experiencing it. Here's a thought experiment to tie this together. Imagine a hypothetical observer existing at the Planck scale, where space-time is quantized and time doesn't flow in any conventional sense. To this observer, the universe wouldn't look like a progression of moments. It would look like a vast, timeless structure of quantum states and relationships. The observer wouldn't perceive a present moment because there would be no emergent time at that scale. Now imagine zooming out, adding more and more particles, allowing thermodynamics and entropy to emerge. Gradually, a concept of time would appear. Events would have an order. Causality would become meaningful. And if you zoomed out far enough to reach the scale of humans, with our billions of neurons processing information and forming memories, the full richness of our experience of time would emerge. The flowing present, the remembered past, the anticipated future. The present moment, then, is a feature of reality at the human scale. It's not fundamental, but it's real. It's defined by the speed of light, which sets the causal structure of space-time, by entropy, which creates the arrow of time, by neural processing, which creates conscious experience, and by the emergent nature of time itself. This brings us to one of the most profound questions we can ask. If the present moment is emergent and relative, if time might not be fundamental, what does this mean for questions of meaning, purpose, and free will? If the future already exists in the block universe, are our choices real? If time is an illusion, what does it mean to live a meaningful life? We'll tackle these questions head-on in the next section. But before we get there, let me leave you with this. The fact that time might be emergent doesn't diminish the importance of how you spend it. If anything, it makes every moment more precious. Because even if time is not fundamental, even if the present moment is a construction, you, as a conscious being, can only ever experience this construction, this moment, this now. Make sure you hit that like button and subscribe, because we're about to explore what all of this means for your life and how you should think about your existence in a universe where the present moment is defined by light speed. So we've journeyed deep into the physics of time, the relativity of simultaneity, the block universe, quantum mechanics, and the possibility that time itself is emergent. Now it's time to bring this back to you personally. How should this understanding change how you live? What does it mean for concepts like free will, choice, and meaning? Let's start with the big one, free will. If the block universe is real, and all moments of time exist equally, does that mean the future is already determined? Are you just an actor following a script that's already written in the four-dimensional structure of space-time? This is one of the oldest questions in philosophy, and the block universe seems to suggest a disturbing answer. Yes, everything is predetermined. Your future actions already exist in space-time, just like your past actions. There's no wiggle room, no real choice. You're going to do what you're going to do, and you are always going to do it. But wait, let's think more carefully about what this means. In the block universe, your future exists, but it exists as a future shaped by your choices. The block includes your decision-making processes, your deliberations, your weighing of options. The future that exists is not independent of your choices. It's the future that results from your choices. Think of it like a recording of a chess game. Once the game is over and recorded, every move is fixed. But that doesn't mean the players didn't make real choices during the game. The recording captures their choices, including their strategic thinking, their mistakes, their brilliance. The block universe is like a recording of all of time. It captures everything, including the real causal processes by which choices are made. Here's another way to think about it. Even in the block universe, causality runs from past to future. Earlier events cause later events. Your current deliberation causes your future action. The fact that the future action exists in the block doesn't make it any less caused by your deliberation. You're not a passive observer of a predetermined future. You're an active participant whose choices shape what that future is. Philosopher Daniel Dennett has written extensively about this. He argues that free will is compatible with determinism. What matters for free will is not whether the future is fixed, but whether your choices are genuinely yours arising from your desires, beliefs, and reasoning processes rather than being imposed from outside. In the block universe, your choices are still yours. They're still caused by your brain's decision-making processes. They're still free in the sense that matters. You could have chosen differently if your desires or beliefs had been different. Some philosophers disagree. Libertarian free will advocates argue that genuine free will requires indeterminism, the ability to have chosen otherwise even with exactly the same prior conditions. Quantum mechanics might provide this indeterminism, since quantum events are fundamentally random. But it's not clear that quantum randomness helps with free will. If your choices are determined by random quantum fluctuations in your brain, are they really your choices? Or are they just dice rolls? My own take is that the block universe doesn't eliminate what's meaningful about choice and agency. Even if my entire life is laid out in spacetime, I still have to live it moment by moment, making decisions based on the information available to me. From my perspective embedded in time, the future is unknown and open. My choices feel real because, from the perspective of my conscious experience, they are real. I don't have access to the block universe from outside. I'm inside it, moving through it, experiencing it sequentially. Here's an analogy. Imagine reading a novel. The entire novel exists as printed text. All the events in the story are already determined by what's written. But as you read, you don't know what's going to happen until you get there. The characters in the story make choices based on their knowledge and desires, and those choices drive the plot forward. The fact that the story is already written doesn't make the characters' choices meaningless within the story. Similarly, the fact that your life is already written in the block universe doesn't make your choices meaningless from your perspective within time. This connects to another profound question. What does it mean to live a meaningful life in a block universe? If everything that's going to happen is already fixed, why bother trying? Why strive? Why work? Why care? The answer is that striving, working, and caring are part of what's in the block. The meaningful life you might live is the one where you do strive and work and care. If you respond to the block universe by becoming passive and nihilistic, that passivity becomes part of your world line. If you respond by doubling down on what matters to you, that commitment becomes part of your world line. The block doesn't tell you what to do. It tells you that whatever you do will be part of the permanent structure of spacetime. I find this oddly empowering. Every moment of your life is eternal. The kindness you show, the work you create, the love you feel, it all exists forever in spacetime. You're not just creating temporary ripples that will fade away. You're etching patterns into the fabric of reality itself. Think about the people you love. In the block universe, every moment you've shared with them exists permanently. The time you spent together isn't gone. It's a permanent part of spacetime. You can't revisit it in the usual sense of time travel, but it's there, eternally real, a fixed part of the structure of the cosmos. This reframes grief in an interesting way. When someone dies, we say we've lost them. But in the block universe, we haven't lost them. Their world line still exists. Every moment of their life is still there in spacetime. What we've lost is the ability to create new shared moments, to extend the region where our world lines intertwine. But the moments we did share, those are permanent. Of course, this is cold comfort when you're grieving. Knowing that past moments exist in the block doesn't replace the desire for future moments that will never come. But there's something profound in the idea that nothing is ever truly lost. The people we love, the experiences we've had, the beauty we've witnessed, it all remains frozen in spacetime, eternally real. Now let's talk about the present moment specifically. We've learned that the present moment is relative, constructed, and emergent. What does this mean for the spiritual and psychological practice of being present? There's a whole tradition in mindfulness, meditation, and contemplative practice that emphasizes the importance of being in the present moment. Be here now, as Ram Dass famously said. The idea is that the past is gone, the future hasn't arrived, and the only real moment is this one right now. We're encouraged to pay attention to the present, to experience it fully, to stop ruminating about the past or worrying about the future. Does the physics we've discussed undermine this practice? If the present moment is just a relative slice of spacetime, if past and future exist equally, why is the present special? I'd argue that physics actually deepens and enriches the practice of being present rather than undermining it. Yes, the present moment is constructed by your brain. Yes, it's relative to your motion through spacetime. Yes, all moments exist equally in the block. But the present moment is still the only moment you're experiencing right now. It's the only moment where you have agency, where you can make choices, where you can pay attention, can respond. The mindfulness tradition isn't claiming that only the present exists in some absolute metaphysical sense. It's pointing out that you can only ever be conscious in the present. You can think about the past, but that thinking happens now. You can plan for the future, but that planning happens now. The present moment is where your life is actually lived. Understanding the physics of time can actually enhance this practice. When you realize that your present moment is a construction, you can appreciate the incredible work your brain is doing to create a coherent experience of now. When you realize that simultaneity is relative, you can appreciate that your now is uniquely yours. When you realize that the speed of light constrains what you can know about the universe, you can appreciate the limitations within which your consciousness operates. There's a meditation practice where you pay attention to the gaps and delays in your perception. You notice the delay between seeing something and recognizing what it is. You notice the constructed nature of your sense of continuous time. You notice how your brain is constantly predicting and updating. This kind of practice is informed by neuroscience, and it reveals the machinery behind the illusion of a seamless present. Far from making the present moment less special, this understanding makes it more miraculous. Out of a timeless four-dimensional block of space-time, out of quantum fields and fundamental particles, out of increasing entropy and neural computation, your consciousness somehow constructs this vivid, immediate experience of now. You are the universe becoming aware of itself, one moment at a time. Here's something else to consider. The speed of light creates a kind of cosmic loneliness, but also a cosmic intimacy. The light cone around your present moment defines what you can possibly know and what can possibly affect you. Events outside your light cone are inaccessible to you. You're causally isolated from them. In a sense, you live inside a bubble defined by the speed of light, a bubble that expands outward from your present moment at 300,000 kilometers per second. But within that bubble, you're connected. Every photon that reaches your eye creates a causal link between you and whatever emitted it. When you look at a star, you're receiving messenger's photons that traveled across space to bring you information. You're touching the past of that star, connecting across spacetime through the medium of light. The speed of light doesn't just isolate, it also connects. It weaves the universe together into a causal network. The same is true of your relationships with other people. Every conversation, every glance, every touch is an exchange of photons and sound waves, particles and forces, creating causal links between your world lines. You can't transcend the speed of light and know what someone is experiencing right now in an absolute sense. But you can be close enough that the delays don't matter, close enough that you're effectively sharing a present through rapid back-and-forth causal connection. In this light, the present moment is not a prison limiting you to an isolated instant. It's a nexus, a point of contact between you and the rest of the universe, mediated by the speed of light. Every photon entering your eye, every sound wave reaching your ear is the universe reaching out to you, saying, "I am here, I exist, I have something to show you." Let me share a personal reflection. Since I've learned about the relativity of simultaneity and the block universe, I found myself relating to time differently. I used to feel anxious about the passage of time, about moments slipping away, about getting older. Now I think of time more spatially. My life is not a series of moments that disappear into nothingness. My life is a path through space-time, and every point on that path exists. I'm not losing moments. I'm adding to my world line. This doesn't mean I'm complacent or lazy. If anything, it makes me more intentional about how I spend my time, because every choice I make becomes part of my permanent world line. The person I am, the things I do, the impact I have, it all gets frozen into the structure of space-time. I can't go back and change the past, but I also don't need to, because the past exists. I can only add to my world line going forward, extending it in directions that matter to me. There's a phrase in physics. The block universe means that the past, present, and future all exist, but we experience them one at a time. I love this because it captures both the eternal nature of time and the experiential reality of flowing through it. You are a being with access to only one slice of the block at a time, but that slice is real, vivid, and full of possibility. Before we move on, let me give you one more thing to think about. We focused a lot on how the speed of light limits us, limits our knowledge, limits simultaneity, limits causal connection. But the speed of light is also what makes the universe comprehensible. If information could travel infinitely fast, if there were no speed limit, cause and effect would become hopelessly tangled. Effects could precede causes. The entire causal structure of reality would collapse. The speed of light is what preserves causality. It's what ensures that the universe makes sense, that we can reason about it, that science is possible. The limitations it imposes are not arbitrary restrictions. They're necessary features of a universe where cause and effect are meaningful. In a strange way, the speed of light is a gift. It creates the structure within which time, causality, consciousness, and meaning can exist. Without it, there would be no arrow of time, no distinction between past and future, no possibility for creatures like us to evolve and contemplate the cosmos. The speed of light doesn't define the present moment despite our intuitions. It defines the present moment in a way that makes our existence possible. So, is the present moment defined by light speed? Yes, absolutely. The speed of light defines the causal structure of space-time, determines the relativity of simultaneity, constrains the flow of information, and ultimately shapes the nature of time itself. But the present moment is also defined by consciousness, by entropy, by neural processing, and by the emergent properties of complex systems. It's a beautiful, multi-layered phenomenon, and understanding it scientifically doesn't diminish it. If anything, it reveals just how remarkable it is, that you're able to experience this moment at all. We've covered an enormous amount of ground, but there's still more to explore. In the next section, we're going to look at some of the cutting-edge experiments and observations that test these ideas. From gravitational wave detectors to atomic clocks on satellites to attempts to detect quantum gravity, we'll see how scientists are actively probing the nature of time and spacetime at the frontiers of knowledge. And we'll ask, what might future discoveries reveal about the present moment? Could we be wrong about the block universe? Could time turn out to be even stranger than we've imagined? Stay tuned, because the future of physics, pun intended, is full of surprises. Now let's explore how scientists are actually testing these ideas about time, simultaneity, and the structure of spacetime. Because everything I've told you so far isn't just theoretical speculation. It's based on real experiments and observations that have been conducted over the past century, and new experiments are pushing the boundaries even further. Let's start with the most precise clocks ever built: atomic clocks. Modern atomic clocks are so accurate that they would only lose or gain about 1 second over hundreds of millions of years. This precision allows scientists to measure tiny relativistic effects that would have been impossible to detect with earlier technology. One of the most famous recent experiments was conducted by physicists James Chinwen Shu and David Wineland at NIST, the National Institute of Standards and Technology, in 2010. They built 2 identical atomic clocks and placed them at different heights, with one clock just 33 centimeters higher than the other. According to general relativity, time passes more slowly in stronger gravitational fields, so the clock at the lower height should tick more slowly than the clock at the higher height. And that's exactly what they found. The height difference of just 33 centimeters, about 1 foot, was enough to create a measurable difference in the rate of time. They also tested velocity-based time dilation by moving one clock back and forth at speeds of just a few meters per second, roughly walking pace. Again, they detected the predicted time dilation. Moving at walking speed is enough to measurably change the rate at which time passes for you compared to someone standing still. Think about what this means for your daily life. When you climb stairs, time literally speeds up for you compared to someone who stays on the ground floor. The effect is minuscule. You'd have to climb stairs constantly for billions of years to notice even a 1 second difference. But it's real. Every time you move, you're changing the rate at which you experience time. GPS satellites provide an even more dramatic example. These satellites orbit about 20,000 kilometers above Earth's surface and travel at about 14,000 kilometers per hour. Both their altitude and their velocity affect how time passes for them compared to clocks on Earth's surface. The gravitational time dilation makes their clocks run about 45 microseconds per day faster than Earth clocks, while their velocity makes their clocks run about 7 microseconds per day slower. The net effect is that GPS satellite clocks run about 38 microseconds per day faster than Earth clocks. If we didn't correct for this effect, GPS would accumulate errors of about 10 kilometers per day, making it completely useless for navigation. Every time you use your phone to navigate, you're relying on corrections for both special and general relativity. The GPS satellites have to constantly adjust their clocks to synchronize with Earth time, compensating for the relativistic effects. Time dilation isn't some abstract theoretical concept. It's an engineering problem that has to be solved for modern technology to work. Now let's talk about gravitational waves, one of the most exciting recent developments in physics. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, detectors made the first direct observation of gravitational waves ripples in spacetime, caused by the collision of 2 black holes 1.3 billion light-years away. This wasn't just a detection of a distant event. It was a detection of spacetime itself, oscillating, stretching, and squeezing as the gravitational wave passed through Earth. Gravitational waves travel at the speed of light, and their detection confirms a key prediction of general relativity. But they also give us a new way to probe the structure of spacetime. When LEGO detects a gravitational wave, it's measuring incredibly tiny distortions in spacetime changes in distance of less than 1,000th the diameter of a proton over a 4-kilometer distance. The fact that we can detect such tiny effects is a testament to human ingenuity, but it's also a window into how spacetime behaves. Here's where it gets really interesting for our discussion about time. Gravitational waves don't just carry energy. They carry information about events in the distant past. When LEGO detected those colliding black holes, the collision had actually happened 1.3 billion years ago. The gravitational waves traveled through spacetime at light speed, and when they reached Earth in 2015, they were messengers from the deep past, bringing us information about an event that occurred when Earth was in the Proterozoic eon, populated only by simple single-celled organisms. This is another dramatic example of how the speed of light defines our present. Every observation we make of the universe is an observation of the past. The farther we look, the deeper into the past we see. When we observe the cosmic microwave background, the afterglow of the Big Bang, we're seeing light that has been traveling for 13.8 billion years. We're seeing the universe as it was just 380,000 years after the Big Bang, when it first became transparent to light. There's something profound about the fact that the past is not just recorded in memories or history books, but is actually out there in the universe, frozen in light and gravitational waves that are still traveling toward us. The universe itself is a time machine, constantly delivering messages from its past. Another cutting-edge area of research is the search for quantum gravity effects. Remember, we don't yet have a complete theory of quantum gravity, but physicists are trying to detect signatures of quantum spacetime at the smallest scales. One approach involves looking for tiny violations of Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant velocities. Some theories of quantum gravity predict that at extremely high energies or very short distances, spacetime might become foamy or grainy, and particles might travel at slightly different speeds depending on their energy. Photons of different energies might travel at very slightly different speeds through this quantum foam. Since the effect would be incredibly tiny, we need to observe photons that have traveled enormous distances to amplify any difference. Gamma-ray bursts, massive explosions from distant galaxies, provide a natural laboratory. These bursts emit photons of vastly different energies all at once. If photons of different energies travel at different speeds due to quantum gravity effects, then photons from a gamma-ray burst billions of light years away should arrive at different times. So far, observations have found no such effect, which places very tight constraints on quantum gravity theories. But the search continues, and future detections might reveal the quantum nature of spacetime. There are also experiments trying to directly detect the granular structure of spacetime. The Fermilab holometer was an experiment designed to look for quantum fluctuations in spacetime itself. Holographic noise that would arise if spacetime is fundamentally pixelated at the Planck scale. The experiment didn't find the predicted signal, but it improved our understanding of the limits on how spacetime can behave at tiny scales. Let's turn to a different kind of experiment, testing the relativity of simultaneity directly. While we can't easily accelerate humans to near-light speeds to test these effects, we can accelerate particles, and we can compare clocks moving at different velocities. One beautiful experiment involved muons, which are particles like heavy electrons. Muons are unstable and decay with a half-life of about 2.2 microseconds when at rest. This means that if you create muons in a laboratory, half of them will decay within 2.2 microseconds. But muons are also created naturally in Earth's upper atmosphere when cosmic rays strike air molecules. These muons travel downward at speeds close to the speed of light. If time dilation weren't real, almost all of these muons would decay before reaching Earth's surface because they're created about 10 kilometers up. And even at light speed, It would take them about 33 microseconds to reach the ground, plenty of time for multiple half-lives to pass. But we detect lots of muons at Earth's surface. Why? Because from the muons' perspective, time is passing more slowly due to their high speed. From our perspective, the muons are living much longer than their 2.2 microsecond half-life because their internal clocks are running slow. From the muons' perspective, time is passing normally, but the distance to Earth's surface is contracted due to length contraction, so they don't have as far to travel. Both perspectives, time dilation from our frame and length contraction from the muons' frame, give the same prediction. Lots of muons reach the ground. This is a direct, everyday confirmation of special relativity. The atmosphere is full of tiny particles experiencing relativistic effects. There have also been attempts to test quantum entanglement over large distances to probe the relationship between quantum mechanics and relativity. In 2017, Chinese scientists used a MISHA satellite to create entangled photon pairs and send them to ground stations separated by over 1,200 kilometers. They confirmed that the photons remained entangled over this enormous distance, and that measuring one instantaneously affected the state of the other, just as quantum mechanics predicts. These experiments probe the nature of non-locality in quantum mechanics. Remember, when two particles are entangled and you measure one, the other's state becomes definite instantaneously, regardless of distance. From the perspective of relativity, instantaneous is ambiguous because simultaneity is relative. Different observers moving at different velocities would disagree about whether the two measurements happened at the same time.